All right, welcome to our third lecture video from our series on Monday, it's April. Gonna keep making that mistake for a minute. April 3rd, where we are now going to discuss what a neutralization reaction is, since we are now equipped with what an acid is and what a base is from our three different perspectives available to us. So in the most simplest sense, a neutralization reaction is what we call an acid-base reaction. Meaning that we have an acid, which is some kind of proton donor, reacting with a base, which is some kind of proton acceptor, in a double displacement reaction. And if there's anything that you take away from understanding what a neutralization reaction is that the products of neutralization are always liquid water, H2O, which you might see me write as HOH, and some kind of soluble ionic salt, which again, that's kind of me being redundant. Salt does not just mean sodium chloride, it means any kind of soluble ionic compound. So anytime we are discussing neutralization, we are always talking about acid plus base yields salt and water, where again, the salt is not limited to just table salts, it could be any soluble ionic compound. So let's practice some examples. So let's look at let's not start there. Let's look at a strong acid and a strong base. So for example, I already wrote that. Let's do one of our 6 strong acids, HClO4 perchloric acid, with magnesium hydroxide. And let's see if we can't figure out the products of this neutralization reaction. We know that we should get H2O and some kind of salt. But let's see if we can't prove that doing our double displacement. So much like we did in our precipitation reactions, I'm going to start by not only just writing out what my reactants are, but also writing out what my reactants are as they exist in solution, meaning I'm going to show these things split up or dissociated into their respective ions so I can figure out what kind of displacement is going on. So perchloric acid, that is going to be my acidic proton, and the perchlorate polyatomic anion. Magnesium hydroxide. Magnesium is a group 2 element, so it creates Mg2 plus ion. And then based on these subscripts here, I need 2 hydroxide anions in solution. And if I wanted to go based on my Arrhenius definition, the HClO4, because it generated the H+, this would be my acid. And my magnesium hydroxide, since it generated my OH- in solution, this would be my base. That's just purely according to the Arrhenius definition. Now, according to my Bronsted-Lowry definition, the base is the proton acceptor and the acid is the proton donor. So this is our acidic proton. And this is going to be donated to our basic particle, which is our hydroxide particle, according to the Arrhenius definition. So H plus donates to OH minus. That means the acid donates H plus to the base. Okay, so now that I know that I'm going to have my H and my OH come together, I'm going to definitely form HOH, which is H2O. And I'm going to keep writing that as HOH. And again, this is simply because I've got H plus come together with OH minus. I need that to come together in a 1-to-1 ratio. So I'm going to write this as HOH, which we know is water liquid. Again, I know it's weird and goes against convention, but I promise writing it as HOH for your at least double displacement reactions is going to be helpful. You can write it as H2O once you're done doing all of your balancing. And then we've got now the kind of other results of our double displacement, which is magnesium, which has a +2 charge, coming together with ClO4 minus, which has a -1 charge. So I need 2 of these in order to create a charge neutral compound. So these are in a 1-to-2 ratio, creating Mg ClO4 2. All right, so then if I'm going to create my balanced overall reaction, I'm going to have H2O liquid and MgClO4 2 aqueous. And we've got to make sure we balance this thing. The way that I like to do this is, again, you know what, here. Let's save this for a net ionic equation. I'm going to leave this HOH so that I can balance hydroxides and H's separately. You can keep it as H2O if that would help you, but I think that this visually helps me personally to try to balance these equations. So for example, like here, I've got 2 hydroxides, but only 1 here, so I need to double this. In doing so, I have doubled not just my hydroxide, but also my acidic H, so I need to then double this so that I now have 2 acidic H's. In doing so, I've doubled my ClO4 minus, but I have 2 ClO4 minuses here. So if I were to write the molecular equation, I would have 2 perchloric acids reacting with magnesium hydroxide to form 2 liquid waters and magnesium perchlorate, which is soluble. And we know this is a neutralization because we've created liquid water and some kind of soluble salt. That is our molecular equation. For practice, why don't we also write our complete ionic equation? And since we've done our double displacement, we should have most of our work done for us. We just now need to make sure that we've included our balancing here. So let's see here. I've got to remind myself that I've got 2 H pluses on my reactant side, and now 2 ClO4 minuses on my reactant side, reacting with magnesium 2 plus ion and 2 hydroxide anions to create H2O liquid, of which there are 2. And then magnesium perchlorate. which is Mg2 plus and 2ClO4 minus. So this is our complete ionic equation, shows everything that's aqueous dissociated into its ions. And then for the net ionic equation, I need to cancel out any spectators, meaning ions that don't contribute to anything interesting that happened, or ions that appear the same on both the reactants and product side of the arrow, or ions that sat around in solution and did nothing. So looking at here what I got, it seems like magnesium was the same both before and after reaction, so that was not involved in any direct chemistry that happened in this solution. Same deal with my two perchlorates. So then now my net ionic equation is 2 H pluses reacting with 2 OH minuses. So 2 acidic protons reacting with 2 hydroxide anions to create 2 units of liquid water. So this is the net ionic equation, and notice everything can be reduced. I mean, I need to keep these twos because that's what allowed me to create charge balance products up here, but all are in a, if I were to simplify it, 1-to-1 ratio. Because if we think about what does it take to make water, that requires 1 H and 1 OH. That would make 1 H2O. So all of these would be in a 1-to-1 ratio. These are all in a 2-to-2 ratio, which simplifies to 1-to-1. And anytime you're looking at a neutralization, all neutralizations will have this in their net ionic equation. Now, you might have a neutralization that also results in a gas evolution, like we looked at with our sodium bicarbonate, right? So you can't just leave that out, right? It's only the spectator ions that are not included in a net ionic equation. But you will always, always, always in a neutralization reaction have H plus with OH minus forming H2O in some kind of ratio that simplifies to a 1-to-1-to-1 ratio. All right, I'm going to break this up. So let's look at another example in our next video of neutralization reactions where we're not looking at strong acids and strong bases. This topic of strong and weak acids and bases and their reactions with one another is extensively covered in 220, but I do just want to show you the convention for how we would write these reactions because we do have that kind of weird partial dissociation strangeness that happens at least in part with our weak acids. So I'm going to split this topic up into two, and then we'll see how we do after that if we have any time for the idea of the acidity and basicity of a solution.